Imagine that you want to build a robot with a camera, motors, navigation software, and perhaps even a robotic arm. Each component may work correctly on its own, but how do we make all these parts communicate and behave like one complete robot? Do we need to create every driver, communication protocol, and control interface from scratch? Fortunately, no. ROS2 gives us tools, reusable software, and a common communication framework. This allows us to spend less time on low level infrastructure and more time building the actual robot application. So, let us begin our ROS2 journey. Hello everyone and welcome to our robot operating system series. In this series, we will learn ROS2 step by step. We will begin with the basic concepts like install the required tools, create our first ROS2 program and gradually move towards practical robot application. But first, what exactly is ROS2? Although its name contains the word operating system, ROS2 is not an operating system like Windows or Ubuntu. ROS2 is a collection of open source libraries, tools and communication mechanisms that help us build robotic application. It normally runs on top of an operating system such as Ubuntu. A simple way to understand ROS2 is to think of it a common language and toolbox for robots. Like a camera produces images, a LiDAR sensor measures distance, a navigation program calculates where the robot should move, and a motor controls driven by the wheels. ROS2 helps these different parts exchange information and work together. Without ROS2, we may need to design the communication between every sensor, program, and controller ourselves. We would also need to decide how messages are structured, how components find each other, and how the system is monitored. ROS2 is already provided much of this foundation. It also gives us access to drivers, algorithms, simulation tools, visualization software, and reusable packages created by the robotics community. This means we can focus more on the interesting question like what should the robot actually do? For example, instead of creating complete navigation system from zero, we can use existing ROS2 navigation tools and adopt them to our robot. Instead of inventing a new communication method between a camera and a perception program, we can connect them using standard ROS2 interfaces. This modular approach works with many type of robots, including robotic arm, autonomous mobile robots, drones, humanoid robots, and research platforms. In this first episode, we will answer three main questions. Why was ROS2 developed when ROS1 is already existed? And what are the ROS2 distributors? And which one will we use in this series? And how does ROS2 connect different robotic components? We will keep the explanation simple today. We will study nodes, topics, services, and other concepts probably in the later episodes. For now, let us begin with the transmission from ROS1 to ROS2. ROS1 played an extremely important role in robotics. It made robotic software more accessible and helped create a large community of students, researchers, developers, and companies. So, why was ROS2 needed? Because the robotics world changed. Robots moved from controlled research laboratory into the factories, warehouses, hospitals, farms, and public environments. Modern robots may use several computers, wireless networks, cloud servers, many sensors, or even multiple robots working together. These systems need more flexible communication and better reliability, improved security options, and stronger support for real world deployment. ROS2 keeps the successful modular idea for ROS but updates the foundation for the modern robotic system. On the left side of the slide, we see ROS1, and ROS1 uses a central ROS master to help different software components discover and connect to each other. This architecture worked very well for the research and many smaller systems. However, a central discovery component can becomes less convenient when a system grows across several computers or multiple robots. And ROS2 uses a distributed communication approach based on DDS, where DDS stands for Data Distribution Service. We do not need the technical details yet. for now, think DDS as a communication technology behind the ROS2. It helps components discover each other and exchange information across a distributed system. ROS2 also gives us a quality of service settings. Usually we are calling as QoS. QoS allow us to adjust how communication behaves depending on the application. For example, a camera may send many images per second. In some cases, receiving the newest image is more important than receiving every older image. And similarly, but an emergency stop command is different. For that message, reliable more delivery may be extremely important. QoS helps us adopt communication to these different situations. The slide also shows topic, service actions and life cycle notes. We will cover these in later episodes, but here is the basic idea. Topics are useful for continuously sharing the information, and services are useful when one component sends a request and expects a response. And actions are useful for longer tasks that may provide progress feedback. Like lifecycle nodes help manage important component states such as configuration, activation, shutdown. And these features give us more structured foundation for building complete robotic system. So that's why we will discover these in detail in future episodes, like what is topic and with a definite examples, and what is a node and how they communicating under the same topic, that we are going to discuss in the future episodes. But for time being, keep this very short. Our real goal is to detect the boxes. For example, plan a path, pick up an object and transport it safely. So like this, we can make a warehouse robot in a simple manner. We do not want to spend the entire project to design communication between every camera, motor, computer and program. So this is not our interest. ROS2 provides a common structure so that we can focus on the application, not on the basic structures. So the same applies to a robotic arm. Even if you take the robotic arm, we can focus on gripping, motion planning and task logic instead of rebuilding every low-level software interface. ROS2 does not remove all engineering challenges. Like sensors still need configuration, hardware still need drivers, and systems still need careful design. But it gives us powerful starting point. Now let us understand ROS2 distributions. You may have seen names such Humble, Iron, Jazzy, or something else. A ROS2 distribution, often shortened we are also calling it as a distro, is a version collection of ROS2 packages and tools. Each distribution provides a stable software environment that developers can install and use it. This idea is similar to Ubuntu release such as Ubuntu 22.04 or Ubuntu 24.04. So similarly, ROS2 distributions also follows an alphabetical naming sequence. So on the slide we can see H stands for humble, and I stands for iron, and J stands for Jazzy, K for tilted, and L for lyrical. So the first letters moved through the alphabets from H, I, J, K and L. So this naming system makes the releases easier to remember and gives each one its own identity. In this series, we will use ROS2 Jazzy together with the Ubuntu 24.04. So why are we staying with one distributor? Because consistency is very important when we are learning. So if everyone uses the same ROS2 distribution and the same Ubuntu version, it becomes easier to follow the installation and commands, packages and examples. And even each distribution is respected to one Ubuntu version. So we cannot swap between these things. So if Jazzy should be installed on Ubuntu 24.04. So that's why first the Linux machine we have to install Ubuntu 24.04 if you target for Jazzy, ROS2 distribution Jazzy. So our setup for this series will therefore be Ubuntu 24.04 and ROS2 Jazzy Jalisco. And we also use the terminator instead of terminal. I will tell you, so which will help us actually work with several terminal windows more comfortably. So this I will explain the installation steps on these tools in the next episodes. Now, does learning Jazzy mean that everything becomes useless when another distribution appears? Actually, no. The main ROS2 workflow remains familiar. So we still create the workspaces, we still use the packages, we still run nodes and build and source our environment. The exact versions supported operating systems. And some commands may change, so we should always check the official documentation for the selected distribution. But once you understand the workflow with Jazzy, adopting to another ROS2 distribution become much easier. Think of it like learning to drive one car. Another car may have a different dashboard, but the general driving principles remains the same. Similarly, if you learn Jazzy, some commands we have to replace instead of Jazzy, humble or some new distribution names. That's it. So, but most of the things remain same. Now, let us look at the central idea behind the ROS2. A robot is rarely controlled by one single program. A real robot normally contains many smaller software components. And the beauty of ROS2 is so we can write some part of the program in Python and some part of the program in C++. So you can communicate between different programming languages. And one component may read the camera, another may read the LiDAR sensor, another may build a map, another may calculate a path, motion planning, another may control the motors. And think another may receive commands from a joystick if you are controlling a robot. In ROS2, these responsibilities are often separated into modular components called nodes. We will study nodes properly later. For now, think of a node as a specialist inside the robot. One specialist handles the camera, one specialist handles the performance of navigation, and one specialist controls the wheels, and one specialist plans the movements. The central ROS2 communication box on the slide is only a visual simplification. It does not mean there is one central server controlling everything, but it represents the communication framework that allows these components to exchange information. Let us follow a simple example. The camera node captures the images and a perception node uses those images to detect the objects. The LiDAR and mapping components helps the robot understand the environment. And the navigation component decides where the robot should go. The planner calculates a route and the controller converts the plan into a movement commands. Finally, the driver sends those commands to the motor. Different components perform different jobs, but ROS2 gives them a common way to communicate. This modularity is extremely useful. If we replace the camera, we may only need to update the camera driver. And if we improve the navigation algorithm, we can work on the navigation component without rebuilding the whole robot. It is similar to building with blocks. Each block has a clear purpose and we connect the blocks to create a complete system. The slide also shows a robotic arm, a autonomous mobile robot and a drone. These robots look and move very differently, but many of their software needs are similar. They all need sensor data, commands, control system, monitoring and communication. For a robotic arm, we may connect perception, motion planning, joint control and gripper control. And if you take for mobile robot, we may connect the LiDAR, mapping and localization, navigation and how the wheel is controlling. For a drone, we may connect camera, positioning sensors, flight control and mission planning. The hardware changes but the modular ROS2 idea remains the same. This is why ROS2 is so powerful and useful. We do not need to begin every robot project from an empty page. We can reuse the drivers, packages and software components. Most importantly, we can focus on this application. For now, remember the simple idea, a robot contains many specialists like nodes and ROS2 helps those specialists communicate and work as one system. That's the main core idea of the ROS2 and its advantages. Now it's a quiz time. Pause the video and write your answers in the comments. Question number 1. Why was ROS2 developed instead of relying only on ROS1? Option A, to remove support for real robots. Option B, to add better reliability, quality of service, scalability and real world deployment support. Option C, to replace Ubuntu with Windows only. Option D, to stop using topics and services. Question number 2. In ROS2, what is the main purpose of a topic? Option A, to store packaged files permanently. Option B, to provide asynchronous message exchange between nodes. Option C, to install a ROS2 distribution. Option D, to replace the operating system. So let us know the answers. For question number 1, the correct answer is B, and question number 2 is also B. That brings us to the end of episode 1. In the next episode, we will move from concepts to practice. We will install ROS to Jazzy and verify the installation and set up a terminator for a better multi-terminal workflow. If this video helped you, please like, comment, share and subscribe. Thank you for watching till here. Have a great day.